Bismillahirrahmanirrahim. Assalamu alaikum viewers. Welcome to my channel once again. And this video is the last part of relating to this topic. And in this video, we are going to learn how to evaluate the integrand, which is of this type. If we are having a function, or what you say, the integrand, if it is of this type, x squared minus a squared, sometimes under the root or sometimes without root. So if they are of this, if you're having f of x of this type or any other variable might be involved, how you're going to replace or what is the replacement of this variable x, which is the independent variable here. So you see, once if you are having a function of this type, and you are going to substitute a sec theta at the place of your independent variable x, or whatever the variable you are using as an independent variable, it depends. Okay, so this is the substitution that we are going to use, plus you can use any angle notation that you like. It's your choice. Okay, you can use phi, you can use alpha, you can use beta, gamma, whatever, omega, whatever you want. So chiefly or conventionally we prefer to use theta over here. That's why we are using. Okay, so this is the last type of our trigonometric substitution, and in this video we are going to cover up evaluate two examples related to this function. So let's have a look and let's see the very first example here. Okay, so here you go, an example. You can see that in the integrand, this entire thing you call it integrand. In the numerator of this integrand, you are having this type. So we are going to substitute a sec theta at the place of our x, wherever we are having x. So remember that this appearance or this format can occur either in the numerator or in the denominator. So there's no such restriction that it is going to be in the numerator like that. Okay, it can be over here in the denominator place as well. So and here a is a constant number, any real number. So and this is something that I've already asserted in my previous video related to the same topic. If you have viewed the first and second part of this video, you might have heard over there. So all right, so let us begin. And over here, let us assume that x is equals to our a sec theta. You can have any number as well over here at this position, but once in this example, you are just provided here constant a as a, so that's why we are using this thing. Okay, now let us now differentiate both sides with respect to the original variable. Okay, so when you differentiate both sides, constant number is always written before the differential operator. Okay, so this is your 1 and it comes out to be a. The derivative of your sec theta is sec theta tan theta. Okay, and that's what we are going to write here. The derivative of your sec theta is sec theta tan theta. And then once you can see that this is a foreign variable, so you're going to apply a chain rule here on this variable, and then this dx will move over here, and you are going to write dx equals to a sec theta tan theta d theta. Okay, so at the place of your dx, you are going to write this stuff. At the place of your x, wherever you are having, you're going to substitute a sec theta over there. So now our integrand is going to look something like this. Something like this. It's going to be a sec theta whole square at the place of your x minus a square upon, at the place of your just x you're going to put a sec theta, and at the place of your dx you're going to write a sec theta tan theta d theta. Alright, you can see here that a sec theta and a sec theta gets cancelled. It's done. And now what is left here is a square sec square theta minus a square tan theta d theta. Now inside the radical, you can see that in the radicand you are having a square common in both the terms of the radicand. You just take it out. We just take it out. This is going to be the stuff, sec square theta minus 1 and tan theta d theta. Now once when this a square comes outside the square root, it becomes a. Okay, so that's it. This is the stuff. Now let's have a look to the relationship between our sec square theta and tan square theta, and after that we are going to make some modification here in this radicand. Let's see. Though I can directly substitute here the formula of your sec square theta and the formula that explains the relationship between tan square theta and sec square theta, but I think that I should put some exhaustive work here. So that's why I'm just picking up the preliminary equation of your trigonometry, and then I'm going to divide entirely with my cos squared theta. It looks something like this. Though it is not part of the solution, but I'm just trying to be a bit exhaustive. This thing is your tan squared theta. So let me continue over here. It's tan squared theta. This thing on cancellation gives you 1. And this is sec squared theta, because you know that it's secant is the reciprocal of your cosecant and all that. So once when I shift this 1 over there, then it tells you that your tan squared theta is equivalent to your sec squared theta minus 1. So now at the place of your sec squared theta minus 1, I'm going to substitute my tan squared theta, alright? So this a under root my tan squared theta dot tan theta d theta, alright? So the square root is going to cancel the square power. You are aware with that. So I'm just having tan theta over here, and this is another tan theta, and on product it gives me tan squared theta. Okay, it gives me tan squared theta d theta. Now I can substitute sec squared minus 1 over here at the place of my tan squared theta, because you know that the integral of tan squared theta is not available. But on the other hand, the integral of secant squared theta is there. So we are going to take the help of it, and we are going to replace our tan squared theta by means of secant squared theta minus 1 d of theta. Okay, now we are going to individually apply the integral in both these terms of the integrand. It something looks like this: secant squared theta d theta minus integral of your d theta, like this. Now the integral of secant square is available, and it is equal to your tan theta. So that's how you can see in the formula list of the integrals for your further confirmation. And the integral of your integrand, if you're having nothing, it means you're having unit integrand here. So whatever the variable is attached with the operator, you simply write that variable after integration. So it is here plus some constant, because this is an indefinite integral. You're not having integral limits here. So once when you get the solution, you just put a constant, you just add some constant over here. So this is the answer of this function. Okay, so that's it. Now let's move ahead to one more example. I hope you have understood this one quite well. Let's move ahead and see another example. So here it is, another example of your third type, relating to your third type. Now here you can observe that with the over here, my f of x instead of f of x is your f of t. Okay, so your f of t, sorry, it's solution. All right, so your f of t over here is something like this, and you just apply your trigonometric substitution that we are discussing right now. You just replace your t by your some constant times sec theta only if it is of this type. If it appears something like this, some constant, whatever the constant is. But over here, along with the t, you're having another constant getting multiplied with it. How you're going to get rid of it? So for that purpose, we are going to do some adjustment inside the radical, or in the integrand actually. So how about if I just divide and multiply entirely my radicand by a square upon a square? Okay, I just divide and multiply this whole thing, this whole radicand, by my a square. Okay, because a square is something that is getting multiplied with t square, and I have to make my t square alone in order to get this format. Okay, so that's why I'm just doing this adjustment, and you see that this a square will be kept as it is. The denominator a square is going to divide these two terms individually like this. Okay, this a square, once when it gets out, it becomes a t cube, and over here now I'm having my t square left, and over here I'm having my b square a square left, that I can also write as my b upon a whole square. Okay, now this is the constant. All right, now you are having a type of this, you are having exactly a format following this type over here. This is a constant, and this is your variable, and it is alone, having one coefficient. So now we are having the available type. We can now apply the substitution. Okay, so actually this integral, which originally given like this to us, we have just transformed it to the third type that we are discussing here in this video by making some suitable and mathematically permissible suppositions. That's it. Now I'm going to replace my t. Let my t is equals to the constant times sec theta. Alright, now I'm going to differentiate both sides with respect to my original variable, which is t. I'm going to differentiate both sides. Okay, b upon a is a constant value, so it is going to be written before the differential operator, and there you go. Okay, so this becomes 1, and is equals to b upon a, your sec theta, tan theta, d theta, alright, upon dt. Alright, this is the chain rule that we have just done. Now shift this dt over here on multiplication with 1, it looks like this. The dt is equals to b upon a times your sec theta, tan theta, d theta. Alright, now you are having what to replace, how to replace dt with what? You're going to replace your dt with this, you're going to replace your t with this stuff. So let's get our desired integrand, and then we are going to evaluate it. Okay, so let's turn the page. So now at the place of my t cube, I'm going to write my b upon a sec theta whole cube. Okay, then I'm going to place my radical square root. At the place of my t square, I'm going to put b upon a sec theta whole square. Okay, minus b square upon a square, as it is going to be copied. And then at the place of my dt, I'm going to write down this whole thing. At the place of my dt, I'm going to write down my b upon a sec theta d tan theta d of theta. Okay, that's it. Excuse me. Now this b upon a and this b cube upon a cube gives me b power 4 upon a power 4, and this is something I'm going to write before my integral sign. It's going to be b4 upon a power 4 outside. What is left here now is sec cube theta, and over here I'm having b square a square sec square theta, b square a square sec square theta minus b square upon a square, and this is sec theta tan theta d theta. Okay, this sec theta on multiplication with this sec cube becomes sec power 4, and this b square upon a square is coming common in this radicand. This on cancellation gives me b power 4 upon a cube. This thing is giving me sec power 4 theta, and over here I'm having b square upon a square common. Inside I'm having secant square theta minus 1 and tan theta d theta. Okay, now this thing is giving me tan square theta, as we have just discussed this in the previous example. So, and when this b square upon a square comes outside the radical, it becomes b upon a, and I'm going to write it before this integral like this because they are constant. And now I am having secant power 4 theta under root tan square theta tan theta d theta. And now over here, this is simply your tan theta b power 5 upon a power 4 on multiplication, and it is secant power 4 theta, and this is your simply tan theta, another tan theta d theta. So this on multiplication give you tangent square theta. All right, so that's the format that we have just obtained, and now we are going to integrate this integral. So what to do now? All right, how we are going to handle this this integrand, which is appeared in the form of a trigonometric functions, how to handle the powers over there. So you know well the relationship between your tan square theta and sec square theta. Let me rewrite it here. It appears like this. Okay, so let us now see how to do and what to do. So an idea comes in my mind that how about if we just break this sec power 4 theta in this way. Okay, and then we break just one sec square theta with our 1 plus tan square theta. We are just going to replace it with the help of this relationship. We simply replace 1 sec square theta by 1 plus tan square theta. Okay, let me turn the page now. So that's how we have just done. Now let us multiply sec square tan square theta with these two terms one by one. So it appears to be like this. Sec square theta tan theta plus this term multiplied by these two. It gives you tan power 4 theta sec square theta d theta. Let us integrate these two functions, which are the part of the integrand, separately. Okay, plus integral, and I just forgot to write my b power 5 upon a power 4. I'm sorry for that. So and okay, now once again we are going to apply simple substitution process in order to get our answers. So if I just, because we know that the derivative of our tangent function is equal to secant square function, so if I just assume that let my tan theta is equal to some variable, you just call it u because you chiefly study u substitution, or otherwise you can use any variable you want, but conventionally you use u, so that's why I'm also using u, though I'm not that much habitual of it. Okay, so once when I differentiate both sides with respect to my previous variable theta, I'm going to get something like this. I'm going to get the derivative of your tangent theta is equal to your secant squared theta, and it is equal to your du upon d theta. So this d theta will go over here, so it comes to be like this. So at the place of your secant squared theta d theta, you're going to replace just d of u. Okay, so let us now do the stuff. Tangent theta is equals to u square du plus integral, it becomes u power 4 du, and you close it. Now let us apply simple integration of our xn. It is going to be plus some constant. So it is now u cube upon 3 plus u power 5 upon 5 plus some constant. Now we are going to restore. Okay, so we know that it is tangent cube theta, and this is going to be tangent power 5 theta. Some constant. Okay, now you see we have just made our substitution with respect to our secant theta, and over here we are having tangent theta. So what to do now? We have to replace this tan by our secant. So you know well that your tan square theta is equals to your sec square theta minus 1. So if I just do what? I need cube theta here. So if I take square root at both sides, first of all, I'm just going to get tan theta is equals to sec square theta minus 1, and I simply write the power of my square root, which is 1 upon 2, and then I apply cube root at both sides. Okay, I'm sorry, I apply cube at both sides. This thing gives me that my tan cube theta is equals to sec square theta minus 1 upon, and not upon, I'm sorry, power cube upon 2. It's not upon, it's nothing. Okay, so tangent cube theta is equals to sec square theta minus 1 power 3 by 2. So I can replace my tangent cube theta by means of this. In the same way, I can replace my tangent 5 theta by means of sec square theta minus 1 5 by 2 power 5 by 2. So that's what we are going to do in the next step. So let's turn the page once again. You're simply eating the page, don't you think? So now b power 5 upon a power 4. It gives me 1 upon 3 secant square theta minus 1 power 3 by 2 plus 1 upon 5 secant square theta minus 1 power 5 by 2. And this is it. Okay, now we have just studied over here. We have just done this thing that our sec theta is equals to at upon b. If you just shift this b upon a on the other side, it gives me that my sec squared theta is equals to at upon b. I'm going to replace my sec theta by at upon b. Okay, so that's what we are going to do now. These pages are getting messed up. So now I'm just coming to the end of this word now. It's 1 upon 3, and it's going to be sec square theta is going to be a square t square upon b square minus 1 power 3 by 2 plus 1 upon 5. The same work I'm going to do here as well. It's going to be a square t square upon b square minus 1 power 5 by 2 plus some constant. That's it. Now we are going to do some LCM work. That's something quite preliminary. It's people are quite well aware of it. So it is going to be a square t square minus b square upon b square power 3 by 2 plus 1 upon 5. It's going to be a square t square minus b square upon b square power 5 by 2 plus some constant. Okay, now you see this 5 by 2 is going to be applied on the numerator as well as on the denominator, and same story is going to be happen here as well. So b power 5 upon a power 4, and it is going to be a square t square minus b square 3 by 2 upon 3 times b square power 3 by 2. Okay, and over here also I'm going to repeat the process, and it's just done, and that's it. It's 5 by 2. So you see, when the powers are overlapped, they get multiplied. This 2 and this 2 gets cancelled. You're having b cube here, and over here you're going to have b power 5. And then I'm going to multiply this constant with this term and with this term and with this term individually. So let's see. We are having b power 5 a square t square minus b square upon 3 by 2 upon 3b cube a power 4 plus, excuse me, and then b power 5 a square t square minus b square 5 by 2 power into 5 times b power 5 a power 4 plus b power 5 upon a power 4 into constant, and that's it. So this and this gets cancelled, this and b square we are going to have in the numerator. So over here we are having b square upon 3 times a power 4 a square t square minus b square 3 by 2 plus 1 upon 5a power 4 a square t square minus b square 5 by 2. And you see this entire thing is a constant. When a constant value multiplied with another constant, you're having still a constant value, some different, but it is constant as well. So we are going to replace this thing by another notation, c prime. You can also use k, whatever you want. So this is the answer of your question. So that's how we just apply the trigonometric substitution. So I hope the concept is at least somewhat clear to you after watching this video to the whole length. And if you feel that this video is helpful in clearing the concept in your mind regarding the topic, then I humbly suggest you subscribe my channel, hit on the like, and share this video as much as you can. And don't forget to put down your feedback in the comment box below. Take good care of yourself, and inshallah just keep on watching my channel for more helpful videos. Allah Hafiz.